Hello, everyone. Welcome to our live question and answer session. My name is Matthew Wenger. I am one of the course staff and instructors in our online classes. We've got Victoria, who's helping out behind the scenes, as well as Alexander. I'm going to hand this over to Professor Impey to welcome everyone, and then we'll get started with your questions, which you can post in the chat. And please just ask those once. We'll grab them from the chat and get them in the queue.
Okay, thanks, Matthew, and welcome everyone for another live Q&A session for the online courses. Ready to take your questions.
Student McLeod, who's on with us live, asks, in your own primary interest of extragalactic astronomy, what question would you most like to have answered?
That's a good question. I think from the work that I did over a period of years on supermassive black holes and the galaxies they reside in and how those two evolve with cosmic time, the question that rises to the top in that field is what were the seeds, what were the seed black holes for this situation? So every galaxy has a black hole, a massive black hole, and this mass of that black hole at the center of the galaxy scales with the old stellar mass. So you have giant elliptical galaxies with lots of old stars that have billion solar mass black holes. A modest mid-type spiral galaxy like the Milky Way has a 4 million solar mass black hole, and so on. But what's not clear is how that all started. Did the galaxy form and then somehow manage to make a small black hole in the interior, or were the seed black holes the remnants of a massive early generation of stars in the universe that then accreted matter around them and formed a galaxy, sort of which was first, the oyster or the pearl? So that's a question I would like to answer.
Excellent, thank you. Tiana Scuto asks, what would happen if we tried to do the double slit experiment, but with virtual photons?
Well, that's a good question. I think you would not have a real experiment because the double slit experiment in the end depends on registering the result of the experiment on a screen and recording it somehow. In the classic version, it would be recorded on a photographic film or plate, and in a modern version, it would be recorded by a photoelectric tube or photomultiplier. So while you might have virtual photons in the early part of the experiment, where they're emitted from a source, maybe a source of virtual photons, and then they pass through one slit or the other, and then combine interferometrically. The question is, how do you record the virtual photon? So the virtual photon has to become real at some point. So I don't think you can do the entire experiment with virtual photons.
The next question is from Rentgen 101. What are your impressions of the Perseverance images so far?
Well, the Perseverance mission is spectacular so far. It was an incredible high degree of difficulty landing. Even more difficult actually than Curiosity some years before, because Perseverance was substantially heavier, even though it was based on the same design and reused a lot of components. It had more instrumentation and a heavier payload. So to do that sky crane landing was spectacular. As for the first wave of images, they are very impressive because, of course, the hardware has had an upgrade. Curiosity had moderately high resolution cameraless. I think the pixel array and resolution of the cameras on the Perseverance rover are at least twice as high, maybe 3 times as high in some situations. Has a greater zoom capability, has 3D video capability, which Curiosity didn't have. So in almost every aspect, both the video and the imaging capabilities of Perseverance are better than anything that's ever landed on Mars.
The next question is from Oriole Sweet, who asks, who's just started taking the course and doesn't have a very specific question, but is puzzled a bit by radioactive decay. So I was wondering if you could explain that a little bit more about radioactive decay and perhaps how it is important in astronomy.
Sure. So radioactive decay is a standard phenomenon in physics where typically massive nuclei, so nuclei at the high end of the periodic table, are unstable. These are nuclei that when you count protons and neutrons, which are roughly equal in most atomic nuclei, become somewhat unequal. And the instability of the nucleus increases with its mass. Iron's the most stable atomic nucleus, so any higher than that in the periodic table, you have the potential for radioactive decay. So as the nucleus becomes more massive, it becomes generally more unstable, and you have the possibility for radioactive decay. The decay can occur in 3 different ways. The nucleus can lose energy through gamma rays, which is one form of radioactive emission, or alpha decay, which is the emission of a helium nucleus, 2 protons and 2 neutrons, or beta decay, which is the emission of an electron. So all of these will slowly change the nucleus to a lighter atomic structure. There's a half-life to this process, which for any particular nucleus is the amount of time it takes half of the atoms in a sample of that material to decay. The half-lives range from billions of years for some isotopes of uranium to very short amounts of time, like weeks and months for some other isotopes. So radioactive decay is a fundamental physics process. It's also important in astronomy in a number of ways. Radioactive decay of iron through nickel is what drives a supernova light curve in the first few weeks or months after the supernova detonates, because you've been creating heavy elements in their isotopes in the supernova explosion. Radioactive decay is also, of course, the way we age date rocks, including rocks we got from the moon, rocks from the outer solar system, which essentially tell us how old the Earth is. So radioactive decay has a role in astronomy in a number of different ways.
The next question is from David Learning, who's on with us live. Would like to know which ancient civilization was the most prolific in astronomy?
That's a good question. And it's a little hard to tell because it's hard to judge because not all the ancient civilizations had a deep understanding of their place in the universe. But as far as observational astronomy, straight observational astronomy, I think the Chinese win that easy, hands down, because essentially the Chinese civilization, which is very long and stable, has generated about 2,000 unbroken years of astronomical observations. The court and the state required astronomy for fortune telling, for looking for omens, or just for keeping track of time. And so there were court astronomers going back a long time, and enormous records were left to us by the Chinese over that period of time. Well, many of them have not yet been fully analyzed or translated into English. So in volume of astronomy information, I would say the Chinese. In terms of sophistication of what they came up with, I think the answer would be the ancient Greeks, of course, because they, at the birth of philosophy and the idea of science as a way of inquiry, they formed some very important ideas about the universe they lived in. They understood that the Earth was round and that it had an enormous size compared to the familiar scales of human existence. And some of the Greeks also jumped ahead to the idea of a heliocentric universe where the Earth was not the center of the universe. They also made crude estimates of the distance to the stars and the planets. And even though they were way off, they were using empirical methods. So on observation, I'd give it to the Chinese, and on theory and conceptual understanding of astronomy, I give it to the Greeks.
Excellent. The next question is from an email. Carrie Lee asks, is everything in the sky essentially the past that we are observing? And if so, why can't we see into the future? And then I'll have a follow-up question after that.
Yeah, it's a good question. And the answer is yes. Everything you're seeing in the sky is in the past. You're seeing the sun as it was 8 minutes ago. And as soon as you start looking at the stars in the night sky, you're looking at light that's years, decades, century, and occasionally millennia old. The nearest and brightest stars in the sky are maybe a few dozens of light years. So that light is a few dozens of years old. But some of the most luminous and distant stars in the sky, including stars you can see in the Orion Nebula, are 1,400 light years away. And so that light was emitted in medieval times. And we can see some stars that are far enough away that we're looking at early civilizations of humanity. So absolutely, everything in the night sky is the past. The reason we can't see into the future is, to put it glibly, it hasn't happened yet. So we have to wait for the one directional arrow of time to move forward into the future for us to experience the future. There's no way to experience it now or review the future from the past.
And then the follow-up question is, since we are seeing into the past, since everything that we are seeing is in the past, does that mean that the Milky Way is at the edge of the Big Bang, accelerating outwards?
That's possible, but in practice, the timescales don't work. So the Milky Way is about 100,000 light years across. And so we're about 2/3 of the way out on one region of the Milky Way. So to the edge nearest our direction in the Milky Way disk, we have about 30,000 light years. To go all the way to the far side of the galaxy is about 70,000 light years. So that number of years, tens of millennia, is a tiny fraction of the age of the universe. And essentially, the universe has not changed substantially in such a small amount of time, less than 100,000 years. So the answer to the question is the cosmic expansion and the global properties of the universe do not change substantially on a time scale like the light travel time across our galaxy.
The next question is from Keith or Crum. We know about the solar system habitable zone, but what can you tell us about the galactic or galaxy habitable zone? What percent does it cover, and what are the implications for life outside our solar system?
The galactic habitable zone is a concept that came up about 10 or 15 years ago. I think it was a group of Australian astronomers that pushed it first and hardest. Charles Lineweaver was one of them. I know him quite well. It's an interesting idea. It's an idea that the galaxy itself has regions that are more or less likely to have biology in them. It's a very crude argument, however, and I think most astrobiologists and astronomers feel that the galactic habitable zone as a concept is of limited utility in predicting where, say, we might or might not find life in the galaxy. But the principle of it is that there's a sweet spot moving out from the center of the disk of our galaxy. Essentially, there's a ring of habitability. If you go too far into the center of our galaxy, the star density goes up, so there are many stars, but also the frequency of stellar interactions and collisions goes up. And so you have situations where solar systems will be unstable. Also, you have a lot of young stars forming, and those young stars will die as supernova, sending out blast waves into a dense region of stars. And that's probably dangerous to life, large amounts of gamma rays and high energy radiation. So the idea is that the dense inner regions of our galaxy are less hospitable to life. Not that it couldn't start there, but there are a lot more hazards to let it be there for a long time and get complex. On the other hand, as you move further out to the periphery of our galaxy, a different issue arises, which is that our galaxy, like other spirals and other galaxies in the universe, has what's called a metallicity gradient. That is a gradient of abundance of heavy elements. And that abundance goes down as you move out through the galaxy. Because of the recycling of elements in stars, gradually stars are enriched in heavy elements, but that process is very inefficient and feeble in the outer parts of the galaxy. So the outer part, the outer ring of the disk of the galaxy, has a lower heavy element abundance than the region we live in or near the center. And the idea is that if that metal abundance or heavy element abundance gets too low, then there's not enough carbon, nitrogen, oxygen, and other trace elements and metals that are required for biology to work. So that's the principle. There's a sweet spot, and too far out, there's not enough heavy elements. Too close in, there are too many hazards. But I think it's not a rule of thumb. I don't think you could really use it to predict in detail where to expect to find life in our galaxy.
The next question is from Exoplanet Exploration, who's on with us live. Is the interstellar medium uniformly nearly empty, or are there irregularities depending on where you are? And what might you find if more concentrations of matter between stars or between galaxies?
The interstellar medium, the space between stars, is actually not uniform at all. It's not homogeneous or uniform. It has variations in density. First, overall, the density is incredibly low. The density is roughly, on average, volume of space, about 1 atom, which means a hydrogen atom, per cubic centimeter. Compare that to the density of the air you're breathing, which is 10 billion times higher. So it's a pretty good vacuum, but it's not completely empty. And it's not uniform because gravity, stellar interactions, and the past history of stars forming in any region has created inhomogeneities. So even in a perfectly smooth gas, eventually irregularities will cause gravity to compress some regions and make other regions less dense. That process is happening, but it's also being stirred up by the stars that form, which when they die as supernova, sweep out cavities of gas. So it's not uniform for that reason. In fact, astronomers have deduced that we live in something called the local bubble. So the density of the interstellar medium right around where we are, near the sun, is actually several times lower than the average interstellar density elsewhere in the galaxy. And it's speculated that this is because a series of supernovae went off millions or even billions of years ago and evacuated essentially a bubble of low density gas by their explosions. We can't see the remnants of these stars. The neutron stars or black holes would be very hard to detect, but we do seem to live in a sort of interstellar bubble within our galaxy.
Thank you. The next question is from Jan Campos, who asks, I guess last week we discussed what's called the collapse of a wave function, and this is a follow-up question about that. So in your description of that, or talking about a collapse of a wave function, is this the many worlds interpretation of quantum mechanics? And is many worlds a metaphor like the cat Schrodinger uses? Can you talk about what many worlds means and if it's a kind of an anthropological description of quantum mechanics?
Many worlds interpretation emerged from Hugh Everett, a physicist in the 1930s and 40s. And that's a very influential idea, but it's pretty much at the realm of philosophy rather than physics. It's the idea that one way of thinking of the matrix of probabilities that attach to any quantum state, where a particle, like an electron, is not at one location, but has a probability of appearing at many locations and a probability distribution of where it is at any given time. Hugh Everett's idea was that that you can specify exactly where an electron is, and that each of the probabilities corresponds to an eventuality in a multiverse, in a branching set of parallel universes. And that's the many world interpretation. So it's quite radical. Every time there's a probability in play in quantum theory, each of the probabilities or eventualities actually occurs in a branching set of universes where that probability of that particular outcome becomes one, because that outcome actually happens. And then it continues to go on as the probabilities branch and branch and branch again. So we have this set of universes branching out endlessly and infinitely from some starting points in the past. It's a philosophical idea because there's no way to decide whether this is the correct view of the universe, since by definition we have ended up moving along one of the paths where the particles all exist in the locations where we measure them to be. So it's a way of finessing the collapse of the wave function. The more conventional quantum theory view would be that the act of observation compresses or collapses the probabilities of the wave function and lets the particle be where we actually measure it.
So Oxbowman asks, where do you see big opportunities in multi-messenger astronomy? What devices are in the near future that will assist in this effort? And then maybe you could talk about what multi-messenger astronomy is.
Multi-messenger astronomy is a term that arose a few years ago to describe the conjunct between electromagnetic ways of measuring a phenomenon in astronomy and non-electromagnetic ways of measuring it. The classic example, and really the birth of the field, came when we had the detection of gravitational waves with LIGO. Now, initially, LIGO events, merging black holes, were not detectable at any wavelength in the electromagnetic spectrum. And so we had very poor information on where those events were. But with the first detection of merging neutron stars, giving not just a gravitational wave signal, but also electromagnetic signals across the spectrum, particularly in X-rays, we had the birth of multi-messenger astronomy, where we can learn about a phenomenon through this wide array of information we get from it. Observations at different electromagnetic wavelengths, such as X-rays, radio waves, optical, and infrared, and in conjunct with that, the gravitational waves. Now, full extension of multi-messenger astronomy would also include other non-electromagnetic carriers of information, such as neutrinos or cosmic rays. And so the general term now includes a set of observations or phenomena in astrophysics where we can get more than just light or electromagnetic radiation. And by combining those different modes of information, we learn a lot more about the situation.
And then, what are some of the big opportunities coming up in the future for multi-messenger?
So the future of multi-messenger astronomy is very promising, and that's because the facilities and tools to execute it are getting better. One of the problems with the first gravitational wave detections from LIGO was that with 2 locations, the localization of the gravitational waves on the sky was very poor, essentially just a big swath of the sky. Quickly, we got the Virgo array working with LIGO, so we had a 3rd detector, and very soon we will have gravity wave machines in Japan and India added to the array. At that point, gravitational waves from events in the future will be localized quite well on the sky. We can then combine them with standard electromagnetic modes of information to home in on the source of these gravitational waves much more quickly and efficiently than we have done up to this point. The other spur to multi-messenger astronomy is that we have more facilities coming online that will detect non-electromagnetic forms of radiation, large cosmic ray capabilities, which are being improved as we speak, and also improvements to our neutrino detection capability. And so these are getting better, and also our electromagnetic sensing of gamma rays, X-rays, and extreme forms of radiation are improving. Our radio telescope capability is going to improve by a factor of 100 with the new arrays that are being built in South Africa and Australia. So multi-messenger astronomy has a very bright future.
Oh, excellent. Well, that sounds very exciting. The next question is an email from Jim Huber, who asks, is the curvature of space an actual physical property of space, or is it only a function of the mathematics of general relativity? If the former, is it observable other than through gravity?
It is an actual property of space. So the curvature of space is a part of the theory, part of the apparatus of general relativity, which connects the density of mass and energy in any region of space or in the entire universe to the curvature of space-time in a particular region or the entire universe. It has a mathematical description in the theory, but the fact that we think it's a real thing is because we use light or electromagnetic radiation as probes of the curvature of space-time. If space-time had no curvature, then light would just travel in straight lines, according to Euclid, linearly and forever. But that's not what we see. We see all sorts of subtle bending, curving of light, even lensing of light, little optical experiments that are formed by curvature of space-time. And each of these deviations from linear travel of light is a representation of the curvature of the space-time that the light is traveling through. So since light is a good probe, I think, and we understand the properties of light, I think we can take this as evidence that space-time really is curved.
The next question is from Wallace Pumpkin, who asks, how do you recommend getting into astrobiology? Are the main options a biology route or a physics route?
Yes, astrobiology is a hybrid field, of course. It combines astronomy with biology and speculates about life in the universe and the places where life might exist or have evolved. The classic route to astrobiology is through astronomy. So there are very few astrobiology programs either at the undergrad or the graduate level, just a handful really. So the most common route to astrobiology is from the standard astronomy route. That is would be a bachelor's in physics or physics in astronomy or astronomy, and then start to do graduate work in biology and geophysics perhaps, and chemistry to turn into an astrobiology concentration as a graduate student. So really it's hard to become branded as an astrobiologist before grad school. There are very few pure graduate programs in astrobiology. University of Washington has a very good one that's been around as long as any. So that's the path. It is much rarer for an astrobiologist to come through the biological route. And that's simply because the biology concentration for an undergrad or a grad student is so densely built around the nature of life on Earth that there's not enough time in the curriculum to explore the possibility of life elsewhere or the variations of biology that might result from different physical conditions. So a standard biology degree doesn't really prepare someone for the astrophysics of biology and how it plays out in the universe.
The next question is from Mark Laufenberg. What methods are currently being employed in the search to define dark matter?
Dark matter's search is now concentrated largely on the physics of root, or the physics approach. So there are a lot of experiments, maybe a dozen or more around the world, mostly located deep underground or in mines to be shielded from particle stray events or random radiation, because the incidence of dark matter collisions that might generate a signal in a detector is very low. So you need to keep your backgrounds very low. And so there is a set of these experiments that are essentially all looking for dark matter by its occasional and rare interactions with normal matter, either collisions that result in the creation of new particles or actual resonance where the dark matter particle collides with an array in a crystal, for example, or a matrix or a gas, and deposits energy in that material, and then we measure that energy. Those are the two different approaches. None has succeeded so far, but they're definitely well enough designed experiments that they're interesting. And if none of them yield success within a few years, we may have to go back to the drawing board on what we think dark matter is.
The next question is from Star Tracker. How can you tell what generation our sun belongs to, and how many more star generations can we expect given what we now know about the future of our universe?
Well, we know our sun is about a third the age of the universe. So when our sun formed 4.5 billion years ago, the universe was almost 10 billion years old. And so we know that the material that the sun formed out of was based on the residue of previous generations of stars. And that's reflected in the fact that the sun has more heavy elements in it than you would expect from a star that formed from pristine material soon after the Big Bang. As for how many generations, that's really hard to tell because stars of different masses live such very different ages. Our sun will be a 10 billion year long main sequence star. So if it was generations like that, then obviously there's only the time for one prior generation before you get the sun. On the other hand, if the sun was substantially made of material left over from massive stars that live short lives, maybe as short as 10 million years, there's obviously time for 1,000 of those massive star generations since the galaxy formed. So it's hard to put a single number on the issue of generations of stars, except that we know that it's multiple. And so an average, a mass-weighted average number of generations for the sun's prior life, where its material came from, might be dozens or perhaps 100 generations.
The next question is from an email. Wendy Traver asks, is it thought that comets are responsible for some of the carbon as well as the water on Earth?
Yes, it is now an idea, and it's been in the news recently, that comets have a lot of carbonaceous material. They have a lot of ices frozen into them too, but they have a lot of carbonaceous material. We know this because we can conduct spectroscopy of comets when they get in the inner solar system, or even some that don't come that close, and we can see the signature of carbon compounds. So yes, if comets had played a role in depositing frozen water and volatile materials on the Earth, on the early Earth, they clearly also had a role of depositing carbon-rich materials. But the Earth was not short of carbon-rich materials anyway, so I'm not sure that the cometary contribution for carbon is anything significant compared to what was already here.
Excellent. The next question is from one of our live participants, Oxbowman. Again, a follow-up question regarding multi-messenger astronomy is that it seems like it's becoming more common to read about multi-messenger astronomy in the literature. And so I don't know if we answered your question, Oxbowman, about why the discipline seems to be increasing in importance, but maybe you could specifically address why you think multi-messenger astronomy is gaining such importance and traction in the literature?
I think it's gaining because gravitational waves are a brand new field of astronomy, just 4 years old, basically. And so this was the spur to multi-messenger astronomy, the act of combining gravitational waves with other forms of detection in electromagnetic waves. And that wasn't possible until 4 years ago. And now it's more possible because the sensitivity of the gravity wave detectors is better, and because we have more gravitational wave observatories in play, which lets you narrow down the position of the source of the gravitational waves. So those are the main reasons why the field is increasing, because the position sensitivity of gravity wave sources is better than it used to be, and the number of gravity wave detections is increasing as the sensitivity of that machine, those machines like LIGO, improves.
Adjacent asks, has astronomy taught us anything new about fundamental sciences like chemistry or physics?
Astronomy and chemistry are, closely related. I don't know that astronomy has taught us anything fundamental about chemistry, because astronomy is chemistry played out in a laboratory that's huge and that we don't control very well. So it's not a controlled experiment. I think most knowledge of chemistry has come from controlled experiments in the laboratory. So in that sense, no, we don't really learn about fundamental chemistry from what happens in the universe. However, we do learn about the potential of chemistry to actuate molecules and create interactions and phenomena that we might not be able to see in the lab or on Earth because of the timescales involved, or the densities or physical conditions that we can't recreate. So it allows us to see much more experimental chemistry than we might have access to on the Earth. The connection to physics is also strong, of course. Fundamental physics does play out in the universe on many different scales, particularly with regard to high energy phenomena, particularly with regard to black holes and their event horizons, and particularly with regard to situations of intense gravity. So in all those cases, astronomy has illuminated our understanding of physics.
The next question is from JL Escalante. At your current level of knowledge, the two questions are, what are you currently working on, and what is the subject that intrigues you the most?
Well, I'm now mostly working on education research with the good group that we have here at the University of Arizona. So I'm mostly working on the project to detect fake science using neural nets, on how to teach online classes better and more effectively, in particular, either at the U of A, so sort of for credit normal university classes for non-science majors, or the free choice equivalent through massive open online classes. So those are the main projects I'm working on right now. I forgot the second half of the question.
The second one is, what subject intrigues you the most?
Oh, the subject that intrigues me, I think, has been for a few years and still is astrobiology, because we are getting so close to the actual detection of life beyond Earth, and it could happen in a number of different ways that, to me, that is still the single most fascinating subject in science.
The next question, I think I skipped over this one accidentally, but Diwakara asks, since you studied in Tibet, what do you think of the Buddha, or what do you think of Buddha's explanation about the universe? Which is older and more accurate?
So I've worked with Tibetan monks and nuns, but I actually haven't been to Tibet. These are Tibetans who are in exile from Tibet, living in India or Nepal or Bhutan, other places I visited. I would like to go to Tibet, but it may not be on the cards, because once you've been very closely associated with the Dalai Lama and Buddhist monks, you probably are not on the Chinese authorities' favorite list. So I forgot the question again.
It's about what do you think of Buddha's explanation of about the universe, and which is older and more accurate?
Right. So the question is about the Buddhist or Buddha's explanation for the universe. And I think it has to be recognized, since this was coming to us from 1.5 millennia ago, that this is not sort of scientific theorizing or speculating in a normal way. The Buddha, in his alleged or attributed writings or sayings, talked about all sorts of things, and was actually mostly interested in the human condition, as I would put it, rather than the nature of the universe. But there was a cosmology and there were astronomical ideas around the time of the Buddha. Not all put out by him, actually. Most were put out by teachers, sometimes before him and sometimes after him. And in this cosmology, the universe is an eternal, endlessly forming and reforming place. And so life is coming into being and going out of being. There are many worlds. There are many worlds that could have life on them, and life could be as sophisticated elsewhere as it is on the Earth. So it's a very expansive cosmology, if you like. But it was not framed as a physical cosmology based in the way a scientist would in the modern era. So we have to view it through that lens.
Excellent. The next question is from Fady911X. How realistic is it to live on Mars in the future?
I think it'll be done, and it may happen in about 30 years, for maybe not forever, but for colonists who will spend some years there and then come back. It's a very challenging environment. It's a very harsh environment. Forget about the fact that it's tens of millions of miles and a good chunk of a year away, and a lot of money in terms of getting someone to and fro from the Earth. So there's no easy going backwards and forwards. There's no bailing out. There's no coming back for a quick visit. So you pretty much have to commit to Mars. And living on Mars with that kind of commitment, multi-year commitment, and maybe forever, is really challenging. We'll never have more than very constrained habitats, either under the surface or built on the surface and protected from the radiation with thick cladding. And so the ability to recreate on Mars, the ability to have your own space, the ability to relax in a different environment is simply not there. You're just going to be contained. People have had struggles during the pandemic just being cooped up for a year. Well, in Mars, you're going to be cooped up for as long as you're there, and cooped up in a more fundamental way, because there's literally nowhere else you can go.
So then the next question is, the follow-up is, will it be for the rich only haven utopia, or by your own breathing oxygen dystopia? What do you think?
It's not clear how it'll go. It'll obviously be only if it's not governments doing it, and NASA of course has plans, and the Chinese have plans. If it's the private sector doing it, then obviously extreme resources will be required to go to Mars or to be one of the colonists, unless they're paying your way, the company that is. So it's certainly possible that the first colonists might be coming through a private sector partnership that requires them to have substantial resources, just as many of the first space tourists spent $10 or $15 million to go up on the Soyuz to the space station, the first dozen space tourists, for example. Maybe a thing like that, even at a higher scale. That's not really utopia, but I don't think it's a dystopia either. I think the first experiments on Mars are going to be so limited, and limited in duration too, and yes, very expensive, that it may well only be very rich people who can do it.
The next question is the final follow-up related to this is planet terraforming feasible? And I mean, we can talk specifically about Mars, but then we can talk about other, possible places like the moon or other, moons.
Right. So terraforming in general is a term for making another planetary body like the Earth in some manner, and hopefully like the Earth enough to live on it without a spacesuit. Terraforming Mars has been well explored. It's extremely challenging, but not in principle impossible. Terraforming other worlds is extremely difficult and much harder. Mars at least has a starting point of being smaller than the Earth, but substantial fraction of the Earth's gravity. So that's one advantage. It has a very thin atmosphere, so you'd have to thicken the atmosphere up with the right ingredients to make it breathable. And you'd have to raise the temperature, of course, for liquid water to exist there. If you ask for those requirements on other objects in the solar system, you have a real problem, because they're either airless bodies with not enough gravity to hold any atmosphere, like the moon, and it really would be essentially impossible to terraform the moon at any reasonable time and cost. Or you have moons in the outer solar system that might be habitable under their surfaces, But again, they can't be rendered Earth-like in any way as far as their surfaces go because they're so far from the sun, the surface temperatures are hundreds of degrees to below zero. So there's no other plausible terraforming target in the solar system, to my mind, than Mars.
And if you think about it, I mean, it's taken us a long time to barely terraform the Earth, and that was, it's habitable already, and we're just taking it from one status of habitable to another status of hopefully habitable. The next question is from, oh no, it's Anna. In the press, I've read that there is new thinking on how dark matter can interact with black holes and or create them. Is this speculative or is this more observational research?
Yeah, I've read these articles too, and I've looked at one of the papers at Spacetime. This is speculative. There's no question that it's speculative. We just don't know enough about dark matter and its properties to speculate on its relationship with black holes. In principle, dark matter interacts so weakly, not just with everything else, but with itself, that it's very hard to imagine how it can be a contributor to black holes in any significant way, although matter that falls in will not get out, dark matter that falls in will not get out, or to alter their properties in any substantial way, just because the density of dark matter in space is quite low. And so the amount of dark matter that might become part of a black hole is also quite small. So really, I think ideas of understanding dark matter better through its interaction with black holes are truly theoretical, and I haven't seen any plausible way to make that into a real experiment.
Keith Crum would like to know, is there increased concern regarding solar cycle 25 since we have many more things in orbit than we did 10 years ago?
Yes, there's concern, of course, because when you hit the sunspot maximum and you have very high levels of high energy radiation and activity caused by interaction with the solar wind, it's a great hazard for sensitive electronics, for telemetry systems, for attitude controls in spacecraft, and of course for telecommunications on Earth. Sunspot cycles are notoriously difficult to predict, and in the modern era, we've not successfully predicted the intensity of any sunspot cycle, certainly not this century. So the prediction of the peak, the next peak valley, or even next few peaks of the sunspot cycle is extremely difficult, and I've seen no reliable way to do it. So we're sort of at the whims of what actually happens.
Photozone, who's on with us live, says, if string theory postulates multi-dimensions, could the reason for the missing antimatter in the universe be explained in one of those dimensions?
Well, it's possible, but antimatter in physics is on an equivalent footing to matter. There's only a very slight asymmetry in the quantum properties of matter compared to antimatter. So string theory would have to pull out another major difference between matter and antimatter that's not manifest in the universe we live in, that the energy is available to us, to say somehow why the dark matter, or sort of the antimatter, was sequestered in hidden dimensions. So I haven't seen any plausible mechanism in string theory for why that may be the case.
And then a related follow-up is, if gravity is a consequence of bending space-time, then why is it that we think it has a particle to carry the force?
It's just a different way of conceiving of gravity. We don't necessarily attribute gravity to the consequence of bending space-time. The things are linked intimately. So mass and energy cause the curvature of space-time, and gravity is what objects experience when there's mass and energy in the situation. And that just describes how they move and how they behave. So I think that's the more appropriate way to look at this.
The next question is from one of our live participants. Oh, it's J.L. Escalante again. So there is a, what do you think about Yusaka Mazawa's invitation to travel to the moon? What do you think are the basic qualifications in a human to go to leave the planet?
The gentleman referred to in the question is a Japanese industrialist, I think, but certainly billionaire, who is wants to go on one of the first commercial ventures to the moon, and he's offering a competition to take people with him where he pays their way, so they don't have to pay. Obviously a very attractive proposition, because paying for a journey to the moon would be many tens of millions of dollars. I haven't seen the web form. I haven't looked at the application form because I'm not particularly interested in that trip through him myself. So I'm not sure what he's looking for. Presumably he's looking for someone who has the excitement of adventure to be able to do this and would be willing to make the most of the experience. I don't think he's trying to be that selective beyond that. He's just interested to see who actually applies.
Student McLeod asks, knowing what you do about the radiation hazards and psychological issues involved in isolation for months, would you personally accept the opportunity to go on a Mars mission?
You know, later in my life, I'm 65, but I hope I still have a few decades left. Yes, I might do it, because if it was just for, dealing with the radiation exposure and the danger of it for a year or so, well, that's a lot of radiation exposure equivalent to a normal, quiet, tranquil life on the Earth, but actually only increases your marginal cancer risk by a small fraction, not by a large factor. The hazard clearly is more that you just will never come back, that it's just a sheer dangerous mission when it hasn't been done before. I might well try it, it depends on who's doing the thing, and I wouldn't probably want to be in the very first. But if there's opportunities and there's a possibility of having your way paid, it's something I might consider, but not as a one-way trip.
Another question is from an email. Does light fade and die when it travels endlessly in the universe?
No, it seems not to. So there was an idea called tired light. It was a physical mechanism that was supposed to be an alternative to redshift, as in the cosmological redshift, where light gets weaker or has lower intensity and longer wavelength as it travels through space-time because of the expansion of the universe. For people who were contemplating other mechanisms and didn't believe in the cosmological redshift, as that's called, they hypothesized the idea of tired light, the fact that just light loses energy through just duration of travel through the vacuum of space. We've seen no evidence that light behaves in this way, and there's actually now some significant constraints against tired light theories. So it looks like light does not change its energy as it travels through space. Now, why does it not? Well, the vacuum, especially a pure vacuum, is by definition empty. So it's empty of interactions with matter or radiation. So there's no clear way to believe that radiation should change its properties moving through such a medium.
Excellent, thank you. The next question is again from an email. What do you make of the experimental tokamak nuclear reactor? Are we in danger of a possible extinction caused by this reactor? Or do you think it will be a boon in energy production? Or do you think it will be more of a research, I guess, just an experiment?
I think the tokamak technology is pretty much just an experiment at this point. It's not clear, and in fact there are signs that it will not lead to a commercially viable fusion reactor. Tokamak is, I think, a Russian originating term, and it implies the toroidal shape of a plasma containment device, where the idea is to contain with a physical structure, but inside that magnetic fields, the plasma that you're trying to get hot enough and dense enough to cause fusion to occur. So tokamak was the technology or the mechanism developed, I think, initially in Russia, but then spreading to the West, and the Americans have tried this too. It's not clear that tokamak is ever going to deliver sustained fusion, and so engineers are now not looking at that design anymore, but actually looking at other designs and ways of getting a sustained fusion reaction, and therefore the energy release associated with that.
Oh, thank you very much. The next question is from Petra, who would like to know, do people age differently in space than they do on Earth?
Yes, and I'll set aside for a minute the fact that they age at a different rate if they're moving at relativistic speeds. Let's just talk about people not moving that fast and in space or near the Earth. They age differently, partly because the environment is so different. Almost every space environment is a high radiation environment, and therefore a high hazard environment in terms of increased mutation rate. And so the aging process definitely depends on mutation, because as the genetic material ages and mutates, it loses some of its resilience or ability to replicate purely, and that becomes a limiting factor. There's something called the Hayflick limit, which is the limit that any cell can subdivide before planned obsolescence takes hold and the cell dies. And it's a number of about 50 or 52. In space, that Hayflick limit would be reduced, and the obsolescence of genetic and cellular material would be increased, or its age reduced, because of intense exposure to radiation, damaging radiation, which essentially damages the genetic material, increases the mutation rate, leads to more difficulty of repair of the DNA, leads to increased incidence of disease, and then if you're in a reproduction situation, of birth defects. So definitely we age differently in space.
All right. We have to wrap up a little early today because we have a team meeting with some students. So this will be our last question for today. But I think it's a great one to end on. Hernan asks, how possible or probable is it that we have sown some kind of microbes, tardigrades, or extremophiles on the moon or Mars with our previous missions, both from the US, Europe, and the USSR, if we don't sterilize the equipment as thoroughly as maybe we do today, or as we should?
It's an interesting question. Has the space program contaminated any other body in its early history? And the reason it's a good question is because, as the question acknowledges, we've not been very good at the decontamination or sterilization path that we now follow. Every Mars mission for the last few years and into the future, designed by NASA, is designed to be sterilizing, self-sterilizing, or sterilized before it leaves. So it would not bring any contaminating organisms to the moon or Mars. But that was not always true during the Apollo era and the first part of the space program. Now, the odds that anything that happened to get to the moon would survive on the moon's surface are extremely low. There's just no sheltered environment. There's not also any nutrients or very tiny amounts of available water. So that is unlikely to be the case, just too harsh an environment. However, for Mars, it is certainly possible for microbes to survive. And we've seen microbes survive in spacecraft in the vacuum of space with ultraviolet radiation all around, but not for very long periods of time. So I give a cautious answer that we almost certainly have not contaminated the moon, or more recently Mars. But until we know more about the extremities of life's capabilities, we may not be absolutely sure. So thanks for your questions on everything from terraforming to cosmology and quantum theory. There's good questions today, as always, and we'll announce our next 2 sessions soon and be back with you next week. Thanks to Matthew and Alexander and Vicky. Bye.